All right, good morning, everyone. Today we're going to be covering a specific data structure. Well, not a data structure, but an algorithm. Our class our module this week will be data structure and algorithm. And today what I want to do is just get us thinking in a deeper level about our code. We've messed around with for loops. We've gotten a good concept of OOP. And we're at the point now where we need to start thinking about our code, not necessarily as how to get it working, but more about how to get it to work the most efficient way. So with that said, the most clear example that we have on this is going to be linear search. So let's say, what is linear search? Before I start breaking it down, does anyone know what linear search is and can explain it to the class?
Is it where we get a list of items or an array and we go from one end to the other uh, one by one until we find it?
Yeah, exactly.
I don't know.
Perfect. Thank you so much, Brian. So just like Brian said, we have a specific memory space that's being occupied by a list. I like to picture everything in my computer as little blocks of space where everything's being utilized. And here inside of this block of space, let's say that I have something living within a list, since we're talking about Python. And it just continues living over and over again. Oh, hello. All right, so here we have my list that's holding a couple of items. And I want to find something inside of this list. Well, just like Brian said, what I would do is I would go and check space one first. If space one didn't work, I would then hop from space one to space two. If space two is also not the answer, I would continue hopping on from one side to the other. Now, what does this sound like? What kind of code would actually make this behavior?
A for loop?
A for loop. So let's take a look at how that looks. All right, so let's say I have a list of numbers. So a list of numbers. And I make that equal to a list of range, I don't know, let's say 100 for now. Okay, well, now what happens if I print my list of numbers? Well, now when I print my list of numbers, we're able to see that I have an actual list of integers that go from 0 all the way to 100. And actually, I'm just going to want it to go from 1 to 100. That way we have exactly 100 slots being occupied. Okay, so I have exactly 100 slots being occupied inside of this list. And I have a list of numbers from 1 to 100. Well, now let's say that I just wanted to find the number 81. Well, I'm inside of a list. So if I wanted to find the number 81, the easiest way to do that, or one would think that the easiest way to do that, is to say for num in list of numbers and say if num is equal to, I think I said 89, then I want to return none, right? That's the behavior that we're talking about here in linear search. Well, it wouldn't be returning because it's not inside of a function. So I guess I could just say print. So now when I run this code, I'm not necessarily going to see that how many seconds it took to actually be able to find that, right? But let's say that I have something called steps here. And that number of steps is initialized at 0, right? I haven't taken any steps until I actually start looking through my list. Well, now, if I iterate through this list, right, I'm going to go ahead and print, or I'm going to go ahead and go up a step. So I'm going to say step plus equals 1, and that is steps, not step. Keyboard, there we go. And then after that, I'm just going to print the steps. So I can take a look here. Well, now this might be, ooh. Okay, so now when I run through it, maybe a better way to picture this would be to do this. Well, now when I run through this, I can see that every time my algorithm runs, it has to take a total of 89 steps before being able to return my actual number and break my algorithm. So that's great. I got a working solution. I was able to iterate through my list, find the number that I'm looking for, and return that number. So now I'm gonna do a quick introduction to this concept named Big O. We're gonna cover it more in depth tomorrow. But Big O is basically an analysis to figure out. Oh, thank you so much, though. I really appreciate it. Yes, I am. Let me go ahead and pause this recording here. Okay, welcome back, everyone. Before we left to our alumni Q&A, we quickly made this list of numbers, and we were trying to demonstrate linear search and its efficiency, right? We made this demonstration here where this black box on the outside is supposed to be a memory space holding a list, right? And this list is holding an item for each individual index within that list. That's great. Well, we talked about linear search. How does linear search work? Linear search looks from left to right, starts at the very beginning and moves all the way to the right and checks each individual box. And then after that, we talked about how that is interpreted in code. And we said that that would be interpreted as a for loop. We wanted to check how many steps are taken every time. And then we wanted to print out our answer. And actually, just to simplify this, let's go ahead and move this in here. Okay, so now when we run our Python script, we can see that our Python script comes out with the steps taken were 89 steps, and the answer given was 89 because that's the number that we were looking for. We were looking for 89. Okay, that was a quick overview of what we covered before we left for a break. Does anyone have any questions at this time? All right, if there are no questions, then let's talk about what exactly this means, right? Let's turn this into a function. Let's say this is a function named linear search. And this function takes in a specific number, and a list. So what I want this function to do is I wanted to take a number. Ooh, and actually let's go ahead and call this target. All right, I want this to take in a number as a target and a list. Now I wanted to iterate through that list to be able to find that target. Okay, and rather than having num equal 89, I'm going to ask if it's equal to the target, and then we can see the number of steps. Okay, great. And let me go ahead and move this down here. And let's say target is equal to 59. Well, now when I call this function of linear search, I'm going to pass it the target, and I'm going to pass it the list of numbers. And when I execute this file, we're going to see that the target is 59. We're going to take 59 steps. And regardless of what number I pass into it, if my list is an ordered list and it's rising, I'm going to take that amount of steps to be able to find my answer. Now, that's great and all, but there's a little bit of a problem here. So let me go ahead and draw this out. So we're going to do a little quick introduction to Big O. And what Big O basically stands for is going to be the time complexity analysis of a problem. We want to know how long will a algorithm take to be able to solve a problem. Well, here on the left side, what it's going to take is the size of input and down below, it would be the time to complete. Okay. Well, now if I'm exercising this linear search method, right? What would exactly be what would this look like? What would this chart look like? So as my size of input is getting higher, the time to complete my algorithm would also be rising, right? The more input I have, the more time it will take for me to find an answer. Does everyone understand that so far? Okay, I see some thumbs up. Awesome. Now, this works. It gives me an answer, and it doesn't necessarily take very long, but it does take my computer a considerable amount of steps to be able to come up with an answer. So what's the problem, right? Why is this not as efficient? Well, let's say that my list of numbers, instead of being 1 to 1001, I mean to 101, let's say it goes up to this many. And instead of looking for the number 59, well, I'm actually looking for the number of 100,000, right? Well, how long is it going to take this time? Well, now it went pretty quick, but if you take a look at the amount of steps, it took me 100,000 steps to be able to find my answer, right? When we think about big O or complexity analysis, we want to think of the worst scenario possible. So the worst scenario possible is where I'm looking for the very end, right? I'm looking for the very end of this list. Well, that means that at the very peak of my algorithm, right here, is where I actually found my answer. Right? It was the biggest amount of input, and it took the longest amount of time to come up with that answer. Okay. Well, now that I know that, how could I make this more efficient? Right? This is an ordered list. And I know it's an ordered list. So maybe instead of starting from left to right, I can actually start in the middle. Right? So let's think about a phone book example. When I take a phone book and I'm looking for somebody in the phone book, I don't start from the letter A and then flip each individual page. If I know that individual that I'm looking for, their name starts with a K, right? Instead, what I would do is I would open up the phone book in the middle and then decide if that middle page, if it's holding an N, well, I know that I got to go left, right? And then I would take a chunk and go left. Maybe I would cut it in the middle again. Maybe I'll just grab a chunk of pages. But the point is that I wouldn't go page by page to be able to find that specific page. So I want to mimic that behavior. Well, in case the phone book example didn't work, let's take a look at a different example. Let's say I have one square. And this one square, I wanted to hold 16 squares inside of it. Well, currently, if I were to do this linear search method, I would have to manually draw 16 squares. They might not be even. They may be in different places. It doesn't look like this is the most efficient way of doing this, right? Okay, well, what could be another approach? Well, instead of drawing out 16 squares individually, what I could do is take my piece of paper here and I could just go from bottom to top, right down the middle. Well, now I have two squares or two rectangles, right? Well, now I could do the same thing crosswise. Now I have four. Okay, so now that I have four, let's say I fold it again, right? What would it look like then? Well, now I would create creases on both of these top sides. And I have 8. If I were to repeat that behavior one more time, I would have a total of 16 squares. And rather than doing 16 different moves, I would have only had to do 4 different moves, right? If you take a manual piece of paper right now and you fold it, you can see that in 4 separate moves, you'll come up with 16 squares. So this is obviously more efficient than doing something like linear search. Well, how do I interpret this as code? Well, in order to interpret this as code, this is known as the binary search. So let's take a look at that example. Let's call this binary search. It's going to take in the same thing. It's going to take in a target. It's going to take in a list. Well, again, I don't want to start from the left side or the right side. I actually want to start from the middle. So I'm going to say that the middle, or let's make it like this. Let's do left is equal to list at index 0. And let's say right is equal to list at index -1. So now I identified my left and my right. Well, what would middle look like? Well, middle would look at the length of the list with a floor division of 2. And that would give me the index of the middle, right? So now that I have the index of the middle, I can actually start creating my problem. So I know my left and my right. I'm going to want to keep track of my steps as well. So let me go ahead and create those steps. And let's see how we can do this, right? We know that we have our left. And rather than knowing this, I know that my left is actually index 0. And I know that my right would be the length of the list -1. And instead of identifying a middle, I can identify my middle within the loop. So how do I do this? Well, I can say while my left is less than or equal to my right, I wanted to conduct this behavior. So I'm saying while my left side is still not the same as my right side, I want to conduct this operation. So first I'm going to go ahead and make my steps go up 1, right? I want my steps to be increased to show how many times this is repeated. Okay. Next, I want to go ahead and determine my middle. Well, my middle would just be my left plus my right. And then I'm actually going to put those in parentheses to make sure that they happen first. And I'm going to divide that by 2. Okay, so now I have my middle determined. And now all I need to do is determine if my middle is actually equal to my target. So I'm going to say if middle is equal to target, then I just simply want to print. I'm going to print the same statement that I had here. So I'm going to copy that. And num doesn't exist, so instead I'm just going to print target. Okay, so that's what happens if I actually find my the number that I'm looking for within my list. Well, now what happens if I don't find it? And my list middle is less than my target. So I know that it's less than my target, so that means that I should be looking to the right. All right, so then if I want to look to the right, then I want to reset what my left is. And I want to make sure that my left is equal to middle plus 1. All right. Finally, the only thing that's left is if my target is greater than my middle, in which case I would want to reset my right. I would want my right to be equal to middle minus 1. Okay, and then finally, if this doesn't work, then I would just return -1. And let me just go ahead and do this print statement instead. So instead, it's just going to take my steps and print out -1 because it wasn't able to find the actual number here. Okay, let's take a look at this visually. All right, again, we have our array or our list. Our list then holds specific memory spaces. Oh, I'm just going to go ahead and do that. Okay. So the first thing I do is I determine my left. So let's grab this one here. So that's my left. Then I determine my right. I have my left and my right that have been determined. Great. Then what I do is I determine which one is my middle. So 3, 4, 5, 6, 7, 8. Okay, so there's 8. 1, 2, 3, 4, 5. So this one right here would be my middle. All right, so now that that's been determined, I'm going to say if my middle is my target, then I just want to return this number. All right, so I'm going to say, let me do different colors here for each individual statement. So if middle equals target, return middle. Okay, awesome. The next part is, well, if middle is less than my target, then I want to reset my left. So let's say, let's do a red arrow here. So if middle is less than target, then my left is equal to middle minus 1. Okay. So what is this saying? This is saying that it was evaluated and I found out that my target is higher than what my middle is. Well, if I find out that my target is higher than my middle, then I want to reset my left. So that my left is to the right, I apologize, not the left. To the right of my middle. So that the next time this while loop iterates through this loop, rather than looking through the entire list all over again, it's just going to look through the right side of the list. And the opposite would be said if the target was less than my middle. Right? I'm essentially just cutting the list in half so that I don't have to look through so many slots. Does anyone have any questions over what this code is doing so far?
So that should be m+1, not -1.
Where are we at here?
For your drawing, I'm sorry.
That's correct, yes. That should be m+1.
For the floor division, because the middle was 4 slots and the away from the left and only 3 from the right, is it because it rounds up with the floor division?
It's always going to round down. And you want to round down because it's better to run over one slot duplicate amount of times than to accidentally cut out one slot and then it's not covered. Does that make sense?
Yeah, so if it was rounding down, and this is like I'm just trying to make sure I understand, it would be the middle would be closer to the left than it would be to the right.
That's
Or
correct.
is that okay?
Awesome. Oh, I see it on the chat. Thank you, Nika. Appreciate it. Yes. So there you go. We have it n+1, and we're able to see what's going on with this binary search. Well, now the question is the binary search actually more efficient? Well, let's take a look. Let's see what binary search does. We're going to pass it the same target, and we're going to pass it the same list of numbers. Well, what happens when I execute my code now? Well, when I execute my code, I can see that my first algorithm, which is linear search, took 1,000 iterations to be able to find the number 1,000. And it seems like my second iteration failed because it returned -1 after 17 iterations. So there's something wrong with my code here.
I think it's the if middle, it's got to be the list at middle. Is that correct?
Thank you so much. Yes, that is correct. Boo. All right. Now I have an infinite loop. Oh, probably want to throw in that break. Okay, there we go. And this is still printing because the while loop. This might be better if it was a return statement. Maybe we'll change this to a return instead. And while we're at it, we'll change this to a return as well. I suddenly forgot to do the multi-cursor. I apologize, everyone. That's embarrassing. You all saw me struggle through that. All right, let's see. Okay, so now we run it, and we can see that it took 1,000 or 100,000 steps to be able to find the answer of 100,000 in our linear search. And it only took 17 steps to be able to find our answer of 100,000 in binary search. It's considerably less, right? Well, let's try a couple of different outputs. What happens if I put something more towards the middle, but not exactly in the middle? Let's say we have the one right next to it. So let's have, what would be the middle there? It would be 50. So let's have 49, 9, 99, 9. Okay. So now if I run this,
You have too many nines. It should be one less.
no, thank you. There you go. So now if I have this, we can see that it took 49,000 steps, 49,999 steps, while in the other, it still only took 17 steps, and it was able to find our answer of 499. Right? Now let's try the very middle. What happens if we do 50? Well, now the very middle, this one took 50,000, while our binary search only took 1 step. Right? We can see how this is changing slowly. And now if we come back here and we took a look at our complexity analysis, well, rather than it growing at the same amount of rate that our input it's growing, it's actually cutting everything in half, and our binary search is only growing by a considerable amount less than our simple search. So now our linear search, if we talk about big O complexity, and we'll go over this a lot more tomorrow, is actually O of n, while our binary search is actually O log of n. We'll cover logs and all of this information tomorrow. It's just important that you guys start seeing this imagery today to prep us for tomorrow's lecture. Okay, does anyone have any questions over what was covered? No, that's a good analysis. That's a good one, DJ. Just bring up bracketing. I was a mortarman, so that's awesome. Okay, so there aren't any questions. Well, now let's talk about the strengths and weaknesses of each one, right? What happens if my list isn't sorted? Right? Which one of these two algorithms would work the most efficient, and would binary search even work if my list wasn't sorted? Well, let's try it out. Let's say that we have a list that just goes over random numbers. None are repetitive though. All right, so there we go. We have our list. Well, now let's say I'm looking for the number 5, right? What would happen when I run these two algorithms? Well, one of them tells me that on the 8th step, it was able to find the number 5, and that makes sense, right? Because it's our last index. But if we take a look at our binary search is telling us that the number 5 doesn't exist. Why is that happening?
Is it
Because
because it's cutting it in half, so it's missing it each time it's looking?
Okay, so it's cutting it in half, but cutting it in half wouldn't necessarily mean that it's missing it, right? What do you think, Edge?
The while loop checks to see if the left is less than the right, and in this list, it's going to find instances where the left is probably bigger than the right. Right?
Right. Our while loop is actively looking, searching for actual input saying, hey, is my left bigger than the right? Right. And if it's not sorted, this logic that I have here for this while loop or these if statements, they wouldn't work. Right. I'm asking it, hey, is my target less than my middle? Well, my target's number 5. But if we take a look at my middle is number 8 because I'm doing a floor division. Well, 5 is less than 8. Right? And because 5 is less than 8, then on its second iteration, it would only look through these 3 numbers. And we know these 3 numbers aren't available. So every time you use binary search, you want to utilize the sorted function. If you know that your algorithm isn't sorted, or your list, sorry, isn't sorted. Once you utilize the sorted function, it's going to automatically sort that list. And once you sort it and you run the example, well, now you can see that 5 steps were taken to find the answer of 5. And in the second spot, 3 steps were taken to find the answer of 5. All right. All we needed to do was sort the list so that our binary search could work efficiently. Does anyone have any questions over that? Go ahead, Tyler.
So that doesn't mean that you can only use binary to search for numbers. Like if you had a list of names that you put in alphabetical order, you could use the same logic. You would just need some different if statements, correct?
Yeah, let's take a look at that. Let's see what that would look like. Let's see how quickly I could come up with names. All right. So there we have a list of names. right? It's not sorted. Well, let's see what that looks like when I run the sorted function. So let's just go ahead and print sorted list of numbers. And maybe we should switch that to names, but for time purposes. Okay, well, once I run it, we can see that it's sorting the names effectively, right? Adam is first, then Francisco, Nika, Nick, Tristan, Tyler, and we have all been sorted. So the starter function is not only able to sort our values in numeric values, but it's also able to sort our values when it comes to alphabetical. Well, now, what can we do here? How would the sort work on the list of name? What is it looking for? Could you expand your question a little bit, Roger? Are you asking how the sorted function works?
I think it was asking like how like it's gonna be sorted, like if it's gonna be sorted alphabetically or not.
Got it.
Um,
Okay, awesome. So we just demonstrated that. If there's anything else to that question, please let me know. But now we can see that our list is actually sorted. Well, now that makes me wonder, is Francisco greater than Adam? I wonder if my program will be able to do something like that. Let's say, is Francisco greater than Adam? What will it say? Oh, probably wanna, there we go. So it tells me it's true. Francisco is greater than Adam. Okay. Well, if I remember correctly, 5 is also greater than 1, right? And when I run my sorted function, that also proves to be true. Okay. So it looks like I don't necessarily need to change my my logic because it's actually able to do comparison as to least or greatest with alpha values, right? Alphabetic values. So let's try to do Tristan and Tyler and see what they do since they have the same first letter. So let's do Tristan greater than Tyler. Okay, and when I run this, I would expect to see false, that Tristan is not greater than Tyler. Okay, so there we go. We see our false. Tristan is not greater than Tyler. And if we were to run this backwards, well, we can see that that comes out to be true. So I don't necessarily need my statements, my if statements to change. I should be able to pass in the same exact parameters and run the same logic. Instances of string and integer. Oh, there you go. Let's say I'm looking for, I don't know, I'm looking for Nick now. All right, does Nick exist inside of this list? Well, we can see that Nick was found in 4 steps, while in our binary search, Nick was found within the first step. Does that answer your question, Tyler?
It does. Thank you.
Of course. Yeah, we can see that we don't need to rewrite any of this code. Once this algorithm is made out, we can use it with both alphabetic values and numeric values. Any other questions? Go ahead, Saul.
Yeah, just to clarify, I just want to make sure I don't miss this. If you're sorting through a list of alphabetical characters, for example, names, when it's a list, it's going to go by alphabetical, but if it's one versus another, is it going to go by number, like length?
One versus another.
Yeah, so you did Tristan is greater or less than Tyler.
Mhm.
And in one instance you got true, in one instance you got false. Is that still looking at the next alphabetical character, or is it looking at the length of the names?
Got it. It's always going to be, once it identifies that it's running an alphabetic comparison, it's going to run through each individual letter. So if it notices that both of them share the same first letter, then it'll move to the second and figure out which one is which one falls first in the alphabet. And that's how it determines greatest or lowest value. Does that answer your question?
Yes, it does. Thank you.
Of course.
If you were to put, say, and use the sort function with like a string value of like numbers and such, would that break the code, or would it still be able to sort the strings, I guess?
Could you ask that question one more time, Athena? I'm not sure I fully understand it.
So if you had it's sorting based off of alphabetical. So I'm wondering, would it not be applicable? Would it break your code if you had sort of a integer, but it was still a string, but it wasn't like these alpha alphabetical inputs, I guess. Does that make any sense? I'm sorry, I'm not great at phrasing the question.
I think it does. So I think what you're saying is, what if my list were string numbers, right? So str num for num in range 1 through, let's say, 10. Right? And that's actually going to print it out sorted.
Sorry, no, I think that's a little bit more complex. I meant more like one, like if you had like one there and then the names and stuff like that, would it still sort like that?
Got it. So if I had like an actual number 1 or
In a string. Yes.
okay, well, let's check that out. Okay, well, when I run it, the first thing that pops up is the actual number, right? It's still a string, but it's able to place it in order. So now here, let's also add a number 2 just so that we can see this working a little better. We can see that it identifies that it's a string, but it still runs a numerical comparison as well, even though it's a string, to give it a greater or a lower value and sort it accordingly. Does that answer your question, Athena?
Yes, thank you.
Of course.
Is that because that when it's running strings, it's defaulting to the ASCII values? Like I know Tristan's been saying that, but I'm just saying like if you did put those in as numbers, would it still do the same thing? It would still treat the numbers by their ASCII values?
Yes, so the way the sorted function is actually working under the hood is going to be by the ASCII values, as you just mentioned. I'm not going to cover the ASCII package because that's a little bit more in depth, and I don't want to cover that until we go into how computer memory works, which will be this Thursday. But this is that's what's going on under the hood. That's a good catch right there. Does that answer your question?
Yeah, thank you.
Of course. Okay, so Andrew has a question on the chat that says, does the sorted function run through the entire list to order it? And yes, it does. So that's the catch, right? If the list isn't already sorted, by running sorted or the sorted function that's comes from Python, I'm essentially already iterating through the entire list to make it fall into order. And we'll talk about how to fix this problem tomorrow once we go, or not tomorrow, I apologize, on Thursday when we start talking about list versus linked list and how to make it more efficient. Awesome. Okay, great. If there are no other questions, I'm going to go ahead and stop the recording now.